Welcome everyone. Today we're diving into Arithmetic Instructions, the mathematical engine that powers every computation in computer architecture. Let's see how processors actually perform calculations at the hardware level. So how do we get from high-level code like C to actual silicon? It's a three-step journey. We start with abstraction, simple operations like A plus B. This gets translated into assembly instructions like ADD, SUB, MUL, and DIV. Finally, these become binary patterns that physical circuits can execute. Each layer builds on the one below it. At the heart of all this is the ALU. Think of it as the calculator inside your CPU. It takes two operands and a control signal, performs the operation, and outputs a result. Its main job is integer arithmetic and logic operations. But here's what's cool. It can even handle complex math like logarithms and trigonometry through clever implementations. The core arithmetic operations are addition, ADD, subtraction, sub, multiplication, MUL, and division, DIV. These form the basis of all computer calculations. Now here's where it gets interesting. We have two ways to implement these operations. Hardware uses dedicated circuits. They're incredibly fast because they're physically built to do one thing. Addition and subtraction get this VIP treatment. But multiplication and division? They're more economical as software using emulation loops. Why? Because building dedicated circuits for them takes up massive chip space, and they're used less frequently. It's all about that speed versus cost trade-off. Let's see multiplication in action. To compute 3 times 4, we simply add 3 to itself, 4 times. Start at 0, add 3, you get 3. Add 3 again, now 6. Then 9. Finally, 12. It's just repeated addition, exactly how you learned it in elementary school, but now happening in silicon. Division works the same way but backwards. To divide 12 by 3, we repeatedly subtract 3 until we hit 0, counting each subtraction. 12 minus 3 is 9, that's 1. Minus 3 again is 6, that's 2. Keep going. 3, 4. The counter tells us the answer, 4. Division equals repeated subtraction. These simple operations are surprisingly important. INC adds 1, DEC subtracts 1. You might think, who cares? But these are crucial for loop counters and memory pointers. When you're iterating through an array or counting iterations, these single instruction operations make your code way more efficient than calling the full ADD or SUB. Where does the ALU store its data? In registers. These are high-speed hardware storage built from flip-flops. Each flip-flop stores 1 bit, and they're synchronized by clock pulses. Here we see an 8-bit register, Q7 through Q0. These are the fastest storage in your entire computer, which is why they're so precious. Want to negate a number? Enter 2's complement. To turn positive 5 into negative 5, first invert all the bits. 0101 becomes 1010. Then add 1, giving us 1011. And boom, that's negative 5 in binary. This technique is why computers can handle negative numbers so elegantly. It's not magic, just clever mathematics. The ALU needs to communicate what happened during operations. That's where flags come in. When addition overflows, like when 1011 plus 0111 produces a result too big for 4 bits, the carry flag gets set. Similarly, when subtraction requires borrowing, the borrow flag activates. These flags let the processor handle errors and multi-precision arithmetic. Let's zoom out. Every instruction follows this cycle. First, fetch. Grab the binary instruction from memory. Second, decode. Translate that binary into control signals. Finally, execute. Activate the ALU, register file, and memory as needed. This happens billions of times per second in modern processors. It's the fundamental rhythm of computation. Here's a crucial distinction. One instruction you write, like C equals A plus B, actually triggers multiple micro-operations under the hood. Register transfer moves the data. ALU activation does the math. Bus control routes the information. Then we write the result back. Modern processors break every instruction into these tiny steps, often executing multiple micro-ops in parallel. That's how they achieve such incredible speed. Let's focus on fetch for a moment. The CPU retrieves binary code from memory through the data bus and loads it into the instruction register. This is the first step of every instruction, getting the command itself into the processor. No fetch, no execution. It's that fundamental. Alright, let's wrap up with 5 key points. 1. The ALU is your dedicated math engine for addition, subtraction, multiplication, and division. 2. Efficiency matters. Hardware circuits are fast, software loops are economical. 3. Storage happens in registers and flip-flops, the fastest memory available. 4. Logic systems like 2's complement and status flags manage state and handle edge cases. And 5. Everything flows through the fetch, decode, execute cycle, the heartbeat of every processor. Thanks for your attention.